Hello, everybody, and welcome to the final lecture, or this, I should say, the last lecture of my Advanced Soil Mechanics series. That doesn't mean that I won't have other lectures that I still need to record and put up here, because I do have some earlier lectures from the course that I haven't recorded yet, that it is my intent to record and to post online for your benefit. This, however, is the part 3 in the final installment of my basic introductory series into critical state soil mechanics. And this lesson right here is kind of my potpourri lesson. This lesson right here means it's just a combination of a whole bunch of things that I hope is going to be useful to you. Now, in part 1, we introduced you to the basic idea or concept behind critical state soil mechanics, where we relate one-dimensional consolidation theory with traditional shear strength theory. In my part 2, I introduce you to a simplistic critical state soil mechanics model that's based on an elliptical yield surface, and we talk about the rules of predicting stress paths from loading using that critical state model. I also pointed you to where in the Boodhoo textbook you can find instructions and examples on predicting strains in those soils as well. For this part 3 lesson, what I intend to do is to just present to you several relationships that I hope you're going to find useful. When I was introduced to the concept of critical state soil mechanics, it was actually after my graduate education, or at least after my master's education, while I was a consultant in industry. And many of my colleagues were just popping these equations out of their hats like candy, and they were coming up with the most amazing relationships to predict what I had previously thought were very difficult to obtain geotechnical parameters. And these colleagues of mine and good friends helped me to learn and understand that the framework, the theory of critical state soil mechanics can be used to derive mechanistically and physically the parameters that I was looking for in many of my geotechnical problems I was trying to solve. So most of these relationships are taken directly from your Boodhoo textbook, of which case, if you don't have it, I think in the part 2 lecture, I reference what it is. It's Soil Mechanics and Foundations by Boodhoo. We're using the 2nd or the 3rd edition in my text class, or in my class, of the 2nd or 3rd edition of the textbook. So if I recommend, that's a good reference for any geotechnical engineer to have on their shelves. In selecting which equations I'm going to share with you, I asked myself this very simple question. Would this relationship have been helpful or useful to me at any point during my career as a geotechnical engineering consultant? And if the answer was yes, then I included it in this lesson. So with that, enjoy this final set of notes that just has a whole bunch of equations of how you can get to some of these valuable and tricky geotechnical engineering parameters from the same parameters that we use in our critical state framework. So here we go. Here in the top equation, in this tau y, what we have here is the yield shear strength of the soil. So this would be the shear strength of the soil when it begins to yield plastically. So bear in mind that for a strain softening soil, a soil that has a peak strength, this value of shear strength corresponds to the peak shear strength. Now, a couple of things to remember. Remember that N here is the slope of the total stress path in PQ space. So it's normally equal to a value of 3 under typical axial compression loading. This P prime Y, that is equal to the mean yield stress of the soil, the effective yield stress of the soil, and this P naught prime, this is equal to the actual mean stress of the soil. Now, if I don't want the yield strength of the soil, but I want the residual strength or the strength associated with large strains, then I can obtain that as the intersection between the critical state line and the effective stress path. And so that is going to correspond to this equation right here. And you'll recall that M is the slope of the critical state line in PQ space. And it's steeper if you're in compression, it's shallower if you are in extension. And in the previous lessons, I give some equations. In I believe the part 1 lesson, I give the equation for how to compute M as a function of friction angle, or the critical state friction angle. Now here's another equation that I hope that you might find useful. Sometimes I struggled knowing whether a soil was strain hardening or strain softening, and the only way that I thought you'd be able to tell is if I went and I performed a lab test on it. But using critical state soil mechanics, we can predict whether a soil is going to be strain hardening or strain softening. And all we're going to do is calculate this value. It's called alpha PCS. And that's just the ratio of the yield strength to the residual strength. And we just take these equations above and divide them by each other, and we come up with this relationship circled down here. And here's how it works. If alpha is greater than 1, then your soil is going to be strain softening. Strain softening, which means it's going to have a peak strength and a lower residual strength. If that difference is very, very large, then you might have a sensitive soil. Now, if alpha is less than 1, the soil is strain hardening. Okay, now here's some relationships to predict whether or not you have an overconsolidated soil that if it fails, it's going to fail in tension. So if you have a heavily overconsolidated soil, it usually fails in tension and not in compression. And you should be able to predict with your soils when this is going to be a problem. And so you can do that using this relationship right here, okay? Where you're going to calculate this value R sub t. Now remember, R is essentially the critical state model version of the overconsolidation ratio of the pre-consolidation mean stress divided by the mean effective stress of the soil. That's what we call R naught. Maybe I should write that out. R naught equals the pre-consolidation mean stress divided by the effective and current mean stress. So first you're going to calculate R sub t, and then you're going to compare your R naught with R sub t. If R naught is greater than R sub t, then you should be prepared that the soil is going to rupture in tension, not in compression. If it's going to rupture in tension, we can rely on critical state soil mechanics to help us predict what the undrained shear strength of that soil is going to be when it ruptures in tension. And all it is 1.5 times the effective mean stress of the soil at that particular depth. So very, very simple. One thing I do need to remind everybody of, though, and I think we get to it in this, no, not in this slide, but I do want to remind, I'm going to go back here, that these relationships that I'm giving you, okay, these relationships are only really effective and only reliable if R naught is less than or equal to 2. And that's for all the relationships in this lecture. If you have R naught that is greater than 2, then you have a heavily overconsolidated soil. And you'll recall from our lesson in part 1 of the critical state model series that the critical state soil mechanics, because it's based on a continuum of soil, and it can't really account for localized shear bands in the soil, which heavily overconsolidated soils have. The critical state model kind of falls apart when you start dealing with heavily overconsolidated soils. So just keep that in mind with all of these relationships. Okay, this is a fun one. Do you remember our lesson where we talked about C over P ratios and Shansep? Well, we can predict the Shansep C over P ratios using a critical state soil mechanics. So the Shansep C over P ratio from an isotropically consolidated undrained triaxial axial compression test is given by this relationship right here. Where again, phi CS is the critical state friction angle. Kappa, you'll recall, is equal to the recompression index from a consolidation curve divided by the natural log of 10. And then lambda is equal to the compression index from a consolidation curve divided by the natural log of 10. And we already explained what R naught is. So with that equation there, you can estimate or approximate what your Shansep shear strength ratios are going to be. Now, if you were more concerned about what the anisotropically consolidated shear strength ratios are going to be for Shansep analysis, then we can modify the equation and develop a relationship that is more specific to anisotropic soils using critical state soil mechanics. And if we throw in some common relationships that engineers use and rely upon our elliptical critical state model that we talked about in part 2, then we can use this relationship right here to approximate the shear strength ratio for anisotropically consolidated soils. Very powerful. Okay, how about getting the undrained shear strength ratio from or for an isotropic consolidation test? So in other words, what if we want the ratio of undrained shear strength from an isotropic, or I'm sorry, from an anisotropic test divided by the undrained shear strength from an isotropic consolidated test? So we explained in previous lessons that we tend to get larger shear strengths if we anisotropically consolidate the soil in this testing. However, it's just a lot more expensive and complex to do, and not all triaxial shear testing apparatuses have the computers and the automation necessary to perform anisotropically consolidated testing. So instead we could use these ratios, which are defined as this alpha K naught sub NC, to approximate what we would get from an anisotropically consolidated triax test, but only perform an isotropically consolidated triax test. So here's the relationship. Again, it's an approximation, but it's going to get us very close to the actual answer. And again, this is all based on our elliptical critical state model that we talked about in the part 2 lesson. So the real value of this is that we can approximate what we get from an anisotropic CU test, but only pay the money to perform an isotropic CU test, which is much more affordable. Okay, so that previous strength ratio, that previous C over P ratio was the C over P ratio for axial compression. What if I wanted the C over P ratio for direct simple shear? You'll recall, let me open up a whiteboard here. I'll get to a new page. You'll recall that if I have the slope, that's a terrible slope. Let's use black too. Okay, if I have a slope and I have a shear failure through that slope, if I look at the soil up near the toe, or I'm sorry, up the head of that slope failure, this is axial compression. If I look at soil here at near the bottom of that rotational failure, I've got the soil. I've got compression going in this direction. So this is more like direct simple shear. And then right here at the toe of the slope, where I now have the soil is pushing in this manner, I now have axial extension. Remember, this is what we call anisotropy in our shear strengths. If I want the direct simple shear strength ratio, or C over P ratio, I can approximate it with this relationship right here. And you'll recall that OCR is equal to my vertical pre-consolidation stress divided by my vertical effective stress, the current effective stress. So these aren't mean stresses, these are just looking at the vertical stresses. So you want to recall from our Shansep lesson that this relationship exists, right? Where this ratio is equal to S times OCR raised to the M power. So we can estimate these parameters S and M for our Shansep analysis directly from critical state soil mechanics using these relationships right here. These equations right here are quite possibly the most useful of all of the equations I'm sharing with you today. So here's the value for S. It's approximately equal to 1/2 times the sine of the critical state friction angle. And then M is simply equal to 1 minus the recompression index divided by the compression index. So very, very valuable stuff. What about estimating the direct simple shear strength from axial compression testing? So if I want the ratio, why would we use this? Well, because not everybody has access to a direct simple shear device. In fact, very few geotechnical labs do. And so we can use this ratio, which is called alpha DSS-I sub C. We can use this ratio to approximate or estimate what we would get if we were to perform an undrained direct simple shear test and approximate it using an undrained isotropically consolidated triaxial shear test. My brain went blank there for a minute. Okay, and it's just a simple ratio. We're just going to approximate it with this relationship right here. Now, as I mentioned before, again, this relationship is only valid for normally consolidated soils or for lightly overconsolidated soils. Remember, this is R0 less than or equal to 2. Okay, if R0 is greater than 2, none of these relationships I'm presenting to you are valid. All right, why don't we relate the drained and the undrained shear strengths to one another? So this would be, this goes back to that fundamental question of, do I design with undrained shear strengths or do I design with drained shear strength. So SU is the undrained shear strength, and tau sub F is the drained shear strength. And the ratio of the two is equal to alpha sub L for drained strengths, and for undrained strengths, it's alpha Y sub L, okay? Oh, I'm sorry, this is for, forgive me, this is residual strengths. Yeah, I got that wrong. This relationship here is for residual large strain strengths, and this relationship right here is for peak strengths, so, or yield strengths. So it depends if we wanted to design for residual strengths or if we want to design for peak strengths, okay? So either way, we're going to use these relationships as they're given here. And how we're going to use them is whichever alpha you're using, if alpha is greater than 1, that implies then that the undrained strength is larger than the drained strength. So then you're going to want to use the drain strength, i.e. the denominator, whichever one you're using, to design. So the drain strength is the critical case. If alpha is less than 1, that means that the denominator is larger than the numerator. And the numerator, i.e. the undrained strengths, are smaller, than the drain strength. So they're critical and you'll design to them. So calculating these values of alpha could be useful to you to know whether drained or undrained strength should govern for your design. All right, do you remember when we spoke about Skempton's pore pressure parameters? Well, using critical state soil mechanics, we can estimate the Skempton A parameter. Now remember, the A parameter corresponds to the change in pore pressure due to undrained shear loading. So we can estimate the Skempton A parameter using this relationship right here from critical state soil mechanics. And using that, we can predict what our actual pore pressures are going to be from shearing, which could be very, very useful. So you'll recall then that if my A parameter is a negative value, that means the soil is trying to dilate during shear, and so that's usually conserved for over-consolidated soils or very dense granular soils. If A is positive, that means the soil is trying to contract when we shear it, and it's generating positive pore pressures. So that would be more like normally consolidated soils or loose granular soils. This is a really useful back of the envelope relationship that I used a lot in practice to get preliminary numbers. And it was to get the preliminary values of my consolidation parameters. So remember that lambda equals C sub C divided by the ln of 10, and kappa equals C sub R divided by the ln of 10. So if I want to approximate what lambda is going to be, or my C sub C, I can approximate it pretty closely using the plasticity index computed from the Atterberg limits of my soil. So the general range for almost all soils is it's going to be equal to about 1.25 to 1.9 times lambda. And the cool thing is, once you start getting a familiarity with your soils in your local area where you consult and practice, you'll be able to narrow these numbers down dramatically, and you'll have a really good idea what the consolidation parameters are before you even do a consolidation test. For me in Salt Lake City, this was the value that I would often use to predict. Then I can also predict what C sub R, the recompression index, is going to be using this relationship. This ratio of kappa divided by lambda for almost all soils varies between 0.1 to 0.25. For my soils in the Salt Lake City area, I would usually approximate it with a value of about 0.2, and that got me in the ballpark range of what we would see when we would actually perform testing. This is the final slide that I'm going to share with you. This is estimating soil stiffness in the field. Now, lots of researchers over the years have shown that the stiffness values or the modulus values that we measure in a lab are almost always lower than the modulus values that we measure in the field. So when we lose that confinement of the soil in the field, we lose some of that stiffness in the soil. And so researchers like Zitinsky, Randolph, and others, they developed relationships that we could use to approximate what's called the effective moduli. The effective meaning they're more representative of the moduli that the soil in the field are actually demonstrating. So here's some relationships hopefully you'll find useful. The maximum effective bulk modulus of the soil in the field can be approximated with this relationship right here. If we want, instead of bulk modulus, the effective Young's modulus for soils in the field, we can approximate it using this relationship right here. And remember that this nu right there is the Poisson's ratio of the soil. If we instead want the effective shear modulus of the soil, we can approximate it using our critical state model with the elliptical yield surface and this relationship right here. So that does it, folks. All of these relationships that I shared with you, hopefully you'll find very useful in your geotechnical engineering practice, and I hope that you'll find opportunities that you'll be able to pull them out and use them on your geotechnical engineering design projects, and we'll have the opportunity to hopefully teach something to your geotechnical colleagues, because I'm sure they'll find these relationships just as useful as you will. So I appreciate your attention and appreciate your participation in this advanced soil mechanics class, and be sure to let me know if you have any questions or concerns. Thanks.